Gen Chem students. Today we're going to be talking all about everything electron configurations, from electrons to orbitals to quantum numbers and everything in between. So before we get started with these different sorts of questions we got going on here, I want us to have a little bit more of a background of how to do electron configurations, what is an orbital, how many different sort of blocks do we have, and everything that really the periodic table tells us, as well as what are quantum numbers. And let's go ahead and actually start there. So when you are identifying a specific electron, you are going to be given a roadmap of sorts, which we are going to get from our quantum numbers. So there are four distinct quantum numbers. There's your principal quantum number, which you'll normally see as n, and it really just represents your energy level that you're on. So it will start generally at 1 and it goes all the way up to 7, where your energy level is representative of what family you're on, or basically what row you are on. So n equals 1 here, n equals 2 at lithium, n equals 3 at sodium, n equals 4 at potassium, and so on and so forth. So that is your principal quantum number, n. Your next quantum number is either called one of two things. It's called your azimuthal number or your angular momentum number. That will normally be represented as an L, and it represents basically what block are we in. What block? Are we in our S block? Are we in our P block, our D block, or our F block? And technically there are other hypothetical blocks, but when looking at our periodic table here, we really just focus on those four. Now, these different values can show us some specific things. So if L equals 0, you know you're going to be in your S block. If L equals 1, you know you're going to be in your P block. If L equals 2, you know you're going to be in your D block. And if L equals 3, you know you're going to be in your F block. Honestly, these are tried and true, and so just memorize that, and it will significantly help you on the exam. Now, there is one little rule though, and that is going to be that your L value cannot be greater than n minus 1. And that will always be true as well. So L cannot be greater than n minus 1. Greater than or equal to n minus 1. All right, your next value is going to be called your magnetic number. It is going to be represented by m sub L, and it is really going to tell you what orbital am I at. And just as kind of Dr. Einstein went over in class, you have all these different types of orbitals. We know an s orbital is typically just going to look like a sphere where your node values amount will increase per energy level you're on. We know our p ones look kind of like these dumbbells, and where there's at least starting with one node, where a node is essentially zero probability 0% chance or probability of finding an electron. That is what your node is, where an orbital is going to be an area where it is high chance or high probability you will find an electron. And then there's also your D and your F orbitals, but they look kind of like funky. When I was in high school, I was like kind of learning them looking like Nickelodeon splatters, but the shape doesn't really matter. We want the concept of them to matter. So that is what your magnetic number is, and your last number is going to be called your spin number or your magnetic spin number. It's represented by m sub S. It tells you essentially if your electron has an upspin or downspin. So if it's up, it has positive 1/2, and if it's down, it has negative 1/2, and those will always be your values. There's nothing really too special about them. One more thing about your magnetic numbers, going back to them, is that they will always be between negative L to positive L. So if they're anywhere lesser than or greater than those values, they cannot be possible. So quantum numbers are severely important. They'll tell you exactly everything you need to know about the positioning of an electron, which subcell it in, what orbital it is in, etc. So now that we've talked about that, let's talk a little bit more about the different blocks. So starting over here with our alkaline metals and our alkaline earth metals, this block right here is what we call our S block. Now I know what you're probably thinking is, well, each one of these has 2, so are we missing one right here? And the answer is yes and no. So yes, it's missing in this positioning right here, but it's also filled by our helium electron right here. So just because helium's not present in our alkaline earth metals, because we know it's a noble gas, it is technically in the S block. That is, however, the only one that is over here on our right side that will be in the S block. Everything else is going to be P block. So S block, where each of these, this run is one row on an energy level that represents one orbital. We always know that one orbital can only hold 2 electrons. So our lithium will represent an electron and our beryllium will represent an electron. Each one represents an electron, essentially, when we're talking about electronic configuration, because electronic configuration is going to be all about essentially a roadmap of sorts to tell you what element you are based off of the electron you are at. All right, so that is our S block. Our next one is going to be our P block, and that is going to be essentially this entire area right here. It starts at n equals 2, whereas our S starts at n equals 1, and it's each energy level, and it is going to be 6 electrons or 3 different orbitals. So again, your L value of N of L equals 1 tells you you're at the P, and M of L can be anywhere from -1, 0 to +1, depending on what subshell you're in. So that's our P block. Next one is our D block. Now D block and F block get a little bit interesting. So our D block is going to be right here, and it is going to start, it appears it starts at N equals 3. But here's one key thing we need to know about the D block, is that really, even though it starts at N equals 4, you're really going to be starting with calling things here 3D. Do I have a good reason for that? No, just memorize it, honestly. So it's going to be 3D, even though it starts at N equals 4. Okay, now let's talk about the F block. But before we do that, one really quick thing. We know that our D level is going to have 5 orbitals, 1, 2, 3, 4, 5, where values can range from -2, +2, -1, 0, +1, +2, etc. Really along those ideas, essentially. And then each one can hold, once again, each orbital can hold 2 electrons, so we are given 10 electrons in our D. So let's review it. An S orbital can hold 2 electrons. Each orbital can only hold 2 electrons, but the S block is only going to be 1 orbital per energy level. Our P block is going to be 3 orbitals per energy level, meaning per energy level it can hold 6 electrons. Our D block is going to have 5 orbitals per energy level, meaning it can hold 10 electrons per energy level. Now the F block is going to have something funny, similarly to how technically the D block starts at N equals 4, but it's really at 3D. The F block here, starting at N equals 5, N equals 6, is going to jump down here to our lanthanides and our actinides down here. And even though it appears it starts at N equals 6, because this goes 55, 56, 57 starting here, even though it looks like it's at N equals 6, it jumps down 2 this time, and it's at N equals 4. So we'll call this 4F. This row we'll call 5F, so on and so forth. Looking at our F block here, we know that there are going to be 7 orbitals, so 14 electrons. 1, 2, 3, 4, 5, 6, 7 orbitals. Where did I mess up in there? 1, 2, 3, 4, 5, 6, 7. Oh, I know why. Here's what's going on. It's because this row technically right here really is, as you can see, they shifted it from our D block here. So really this is 1, 2, 3, 4, 5, 6, 7 electrons. So for the F block per energy level, you can have 14 electrons or 7 orbitals. So that's kind of how you navigate your periodic table in terms of quantum numbers and orbitals and understanding everything like that. So that being said, let's jump right into these questions and get them done. First question was the maximum number of electrons that can occupy the N equals 4 energy level. So we go to N equals 4 on our periodic table. We know we are going to have our S block of 1 orbital, so we know that's 2 electrons from there. Now, let's jump over then to our P block at N equals 4. That is going to be 6 electrons here. Remember that with the D block, this looks like it's at N equals 4, but it's really N equals 3, so our N equals 4 one's going to be here. And that is going to give us 10 electrons. 10 electrons from our D block. And remember, even though this one looks like it starts at N equals 6 for our F block, it's really at n equals 4, and so that's going to be another 14 electrons from our F block. So S will give us 2, P will give us 6, our D will give us 10, and our F will give us 14. All that will add up to be 32 electrons at the n equals 4 energy level. Next question, how many electrons in an atom can have the quantum numbers n equals 3, L equals 2? Well, n equals 3 tells us what energy level we're at, L equals 2 tells us what block we're at. Where we memorize that L equals 2 tells us we are at in a D block. So we know, I'm going to erase some stuff here. There, that's good enough. We know we're at n equals 3, but we are at L equals 2. And so we know we are here because, again, the D starts at, even though it looks like it starts with 4s2 and then 4d, it's really 3d then. So that is what L equals 2 is going to tell us. So we know that we can have 10 electrons based off L equals 2, telling us we are at the D block. All right, next question. How many orbitals are found in the 5f sublevel? 5f is going to be this one right here. And it asks us, how many orbitals? Well, we know we can have 14 electrons per F energy level, so we know that the answer is going to be 14 electrons or 7 orbitals, because each orbital can only hold 2 electrons. Okay, next question. Which set of quantum numbers for an atom cannot exist and why? All right, we have 3 different sets here, and let's evaluate. All right, n equals 4. That is definitely a valid energy level. L equals 3. Yes, you can have that because remember that L can be anything that is less than or equal to n minus 1. M of L equals negative 3. That's definitely valid as well because we remember our M of L has to be between negative L to positive L. So that is going to be a good one, and we know that our M of S is always plus or minus 1/2, so this one is valid. Next one. N equals 2. Yes, that's valid because we know it's a valid energy level. L equals 2. This is not valid because our L has to be greater, less than, or equal to n minus 1. So it'd have to be 1. So that is why this one is incorrect. All right, and then set 3. N equals 2. All right, yep, absolutely valid. L equals 0. Yes, because it is less than or equal to n minus 1. But typically, we normally let it just fall exactly with our n minus 1, but yes, that is true. And then M of L equals 0, yes, that's true, because it's between negative L to positive L, and well, we only have one value for L of 0, so that's going to be correct. And yes, our M of S is also correct. So your answer will be set 2 is the one that cannot exist because of your L value here. All right, next question. What is the maximum number of electrons that can occupy the 4s sublevel? All right, it tells us exactly which energy level we're at and what subblock we're at. And as for the maximum amount of electrons, well, we know that per S sublevel, and we are at, let's see, we are at the 4s. So we are right here, because again, this n equals 3 corresponded to our D, but we're really at n equals 4 for our S. And so that is 1 orbital, so it is going to be 2 electrons. What is the value of the angular momentum quantum number for an electron in a 6f orbital? Well, we know that n, our principal number, is going to be equal to 6. We know our L, because it's F, is going to be equal to 3. And that will be your answer because that is your angular momentum or your azimuthal quantum number. All right, what is the number of sublevels? So that was your answer. And what is the number of sublevels and the n equals 5 energy level? I'm guessing that's just n equals 5. I'm guessing your sublevels corresponding to your different energy levels. So you'll have n equals 5, but you can also have, if it was acting more specifically about the blocks you can have your S block, you can have your P block, you can have your D block, and you can have your F block, all at the n equals 5 energy level, if that's what that is asking. I think you'd be given more specifics on a type of question like this. All right, how many electrons in an atom can have the quantum number set n equals 4, L equals 3, M of L equals negative 2? N equals 4 tells us we are at the 4th energy level. So we know we could have anything from, we know we could have an S, a P, a D, or an F. Those are all valid at the n equals 4 energy level. L equals 3 is going to specify us a little further. We know that L equals 3 is going to correspond directly with our F because we memorized that with our F block. So now we're narrowed down to, we could have 14 different electrons we're looking at. But our magnetic number here is going to further narrow us in, because remember, your magnetic number tells you what orbital you're in. And how many electrons can occupy an orbital? 2. So we know that we are somewhere in the F block within some orbital that can hold 2 electrons. How do we know if it's 1 electron? We'd have to use our 4th magnetic number that tells us either plus or minus 1/2. But this one tells us that we can have 2 electrons given 3 quantum numbers. So 2 is your answer. All right, was the maximum number of electrons that can occupy the n equals 2 energy level? Well, let's go ahead and look at that. At n equals 2, this is n equals 2. You could have an s, so you could have 2 electrons from there. You could have an s orbital, and you could have 3 p orbitals, so 6 from that, and you don't have any d or any f orbitals, so that answer is going to be your 2 plus your 6, so that's going to be 8 electrons can be in your n equals 2 energy level. All right, everyone, and last thing we're going to cover for the video is practicing how to write different electron configurations, both in expanded and condensed version using noble gases, essentially. So let's go ahead and dive right into that. Let's just go ahead and do a few practice ones. Just remembering, in our S block, you would go where our hydrogen is 1s1. Our beryllium here would be 2s2. So like our hydrogen is 1s1, that means our helium is 1s2, where the 2 corresponds to the second electron within that s orbital. And then you're going to do 2s1, 2s2. Then you jump over here to 2p1 all the way up to 2p6. Your first number corresponding to your energy level. Your second one that's kind of in like an exponential form corresponding to which electron you're talking about within that subblock. So let's do some practice ones. We will do phosphorus, both in expanded and condensed version. We will do bromine. We will do, zirconium. We will also do molybdenum, because it is kind of a weird one, and we'll also do silver because it's kind of a weird one, and then we'll do neodymium so that we can get some F block practice as well. So let's go ahead and start with our easiest one. That's going to be our phosphorus. Phosphorus, okay, we know we're going to have to get all the way through that first s block here, so that first s orbital, so we know we're all the way at least through 1s2. We then get through the second s, so at 2s2, we get all the way through there, 2s2 being up to beryllium. We then get through 2p6, we then get through 2p6, all the way up through our neon, 2p6, again, where we know it's 2p6 because this is 1, 2, 3, 4, 5, 6, within the p block, within the second energy level. We then get through our sodium and our magnesium, so we are through 3s2. And we then get through up to our aluminum, our silicon, and then we're at our phosphorus. So that is going to be at 3p3. We could write this as a condensed version using the last noble gas that was filled all the way, which is going to be our neon. We could do where neon is all the way up through our 2p6, so we could do bracket neon, and then you just write in the remaining ones that are not within neon, so 3s2, 3p3. So that's what it is for phosphorus. All right, let's do the next one then. All right, next one here. So, all right, yep, we're done with phosphorus. Let's erase everything related to that. And let's then next do our bromine. Okay, bromine. We'll do the whole thing. So, all right, we know it's going to be 1s2, 2s2, 2p6, 3s2, 3p. Yep, and again, just kind of speeding through it. 1s2, 2s2, 2p6, 3s2, 3p6. Then we're going to be at 4s2. And then remember, the D block jumps down to 3d, so then we are at all the way through 3d10. Then you jump back up for your P block all the way up to 4p, and it's going to be at 4p5 for our bromine. If we were to do the condensed version, we would use, again, the last halogen corresponding all the way up through our 3p6, which is going to be our argon. So bracket argon, we would be at 4s2, 3d10, 4p5. And that's how you do bromine. All right, next one. And erasing stuff along the way. Okay, let's do our zirconium then. All right, zirconium is going to get us all the way up through to our 5th energy level. So let's speed through this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d. All right, so let's just do that with our highlighter here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and now we are at 4d2. All right, and if we were to do that in condensed version, it would get us all the way up through our 4p6, which is going to be our krypton. So bracket krypton, which is technically its electron configuration again is all that underlined stuff, and then at 5s2, 4d10. Okay, and let's do our next one now, folks. So erase, 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 erase. Oops, that's not what I wanted to do. All right, we'll erase this one and we'll erase this one. Okay, let's do our 2 weird exception ones now. So that is going to be our molybdenum. Now, remember what Dr. Anson was talking about in class, why these ones are weird exceptions, is because let's draw out a block here. So this will be at our, let's see, 1, 2, 3, 4, 5, and this will be at our 4D. And that's because where does molybdenum look like right now? It looks like, oh, and we also need to draw our 5s. So this will be our 5s here. Orbitals represented by the lines. So right now molybdenum is all the way up through 5s2, so 1, 2, and it looks like it is at 4d4, right? 1, 2, 3, 4. Now, molybdenum is really close to having a half-filled, basically it's close to having a half-filled D block. And it is going to actually be more stable being a half-filled D block than having a full S block and a partially half-filled D block. So it is actually going to take one of these electrons from our S block here, and it's going to give it to our D, so that it will look like this now. 1, 2, 3, 4, 5. So it's half-filled, and then our S would be missing one. So now let's write out the full thing for our molybdenum, which is really close to our zirconium, so let's just go ahead and write this in condensed version. Kr, and it looks like, again, it looks like it'd be at 5s2, 4d4, right? No. What we do is we take 1 from our 5s, so it's going to be at 5s1, 4d5, and it's more stable that way. You can probably guess what our silver's then going to be. Our silver looks like this right now. 5s, 1, 2, 3, 4, 5, 4d. It looks like a completely filled 5s, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. But it also wants to be more stable, having a full D block, so it's actually going to take, once again, one of those electrons from our 5s and give it to the 4d. So silver is going to look like bracket krypton, 5s1, 4d10. Alrighty. And lastly, let's go ahead and do our neodymium, which is going to be a lanthanide, which is going to be within the F block. So let's do the full thing, and then we will do the condensed version. So ND, we're just going to speed through this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. All right, we getting there? Good. Now we're up to 6s2. Okay, so 6s2. So we are now, let's just rerun this here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. And then you drop to your F block. 1, 2, 3, 4, and you are going to be at your 4F4. And that is going to be your electronic configuration for neodymium. Perfect. All right, so that is a great example of how to do electronic configurations, both in expanded and condensed version. If you guys have any questions, just let me know. Let's do this one for neodymium really quick. And D is going to be bracket the last noble gas, which is in this case going to be that xenon. Bracket xenon. And it's going to be at that 6s2, 4F4. All right, you guys have a good evening, and you are going to ace your Gen Chem 2 exam. Have a good night.